let's see, there are maybe questions in the chat as well, but let's start with the one here. The first is Anupam.
First of all, thanks to all the speakers, and including Nima and also Witten. So I have a question for, I think, both of them in some sense, because they're related. So as we envisaged our quantum field theory, the energy that we have seen, or whatever we have seen from in the sky to the LHC, essentially local quantum field theory works extremely, extremely well. But what happens if I open up this door of non-locality, non-local aspects of quantum field theory, or maybe not, it's not even a quantum field theory, in the UV and in the extreme IR? And this is the part which we have never seen. And what would go wrong, or what would perhaps we will gain if we give up the concept of locality? So maybe Nima can answer, and then maybe Ed can also answer later.
Maybe I can say something quickly, which is that that it is impossible to make just abstract statements, right? You have to like take particular examples and see how they work. But what I can say, what's the problem? Saying the word non-locality is not as easy as you think. For example, you can do things like adding terms to a Lagrangian looks like 1 over box. Say, aha, I've done something non-local there. But things like that are relatively dumb, because they're secretly having integrated out something which is a normal locally coupled massless particle. Okay, so first, there can be things that look like they might be non-local, but were actually local. You just integrated something out light that you shouldn't have. Beyond that, I would say, but if you do random things that are non-local, the problem is that in a Lorentz invariant theory, non-local, in a Euclidean theory, non-local means, stretching out over some distance, right? But in a theory with space and time, non-locality has no reason to restrict itself to only be backwards in time. Okay, so you also run into difficulties with acausality if you try to do things that are non-local in a random way. But there are examples, and actually Edward referred to one of them, and maybe I'll leave it to him to say more about it. Instead of just sort of randomly saying things aren't local, you have to find interesting examples of things that seem to slightly violate the rules, the standard rules. So there are these standard rules that we think encode causality and locality in amplitudes. And there are examples of theories, at least in 1+1 dimensions, that violate those rules a little bit. These are associated with these TT bar deformations and so on. So these are some examples of theories that don't quite look like normal local quantum field theories exactly in the usual way in the ultraviolet, but don't badly violate the rules that go into building the S matrix. Whether or not theories like that make sense in more than 1+1 dimensions, 1+1 dimensions is so special that I find it very hard to take any general lessons about life from 1+1 dimensions. I think you can use examples from 1+1 dimensions to illustrate any polemical point you want to make about physics. So I'm very uninterested in theories in 1+1 dimensions personally, but in higher dimensions, if one could find examples like that, that would be fascinating.
Remember Weinberg's points in the last 2 lectures I summarized was that any relativistic Lorentz invariant and physically sensible, by which his cluster decomposition was his way to say physically sensible theory, looks like a local quantum field theory at low energies. And although it's not a true theorem, as Weinberg always emphasized, I believe it's true.
Yeah.
Any departure from that, any way to make a physically sensible quantum mechanical Lorentz invariant theory that doesn't look like a local quantum field theory at long distances would be extremely important. Assuming that Weinberg's folk theorem is true, I'll interpret your question as being, what can we do microscopically? And I'll only say, as Nima said, that it's very hard to do anything sensible. Both the TT bar deformation and string theory are examples that probably are something in that category, but I think the only thing I'll add is that you have to replace locality with something.
Right.
You can't just throw it away.
I should say that this is a historical point. It has never happened to us in physics that progress has happened by taking the previous rules and just saying, aha, look how brave I am. I'm crossing one of them out. always we learn things that are more rigid than they were before. They never get less rigid. We never lose principles. We sort of gain them. They get more rigid, more constrained. So even, for example, when we say that string theory is somehow deforms away from field theory at high energy, the high energy behavior amplitudes in string theory is softer, it's different than what we can get in local quantum field theory. It actually saturates what you're allowed to do compatible with the principles of analyticity and so on. So in fact, local quantum field theory was a little too lazy. It could have done something like sharper and better. And string theory does that sharper and better thing when it comes to satisfying the sort of principles of analyticity and causality and so on. So it isn't like you find something which is like, aha, out of left field, you just cross out something and start over. It has never happened that way in 4 centuries. I've seen no reason to expect it's going to start happening that way now.
Then there's a question by Chester.
Yes, hello. And thank you everybody for the very fun talks. Nima, I have a question about this general approach to treating the scattering amplitude as the fundamental object. It seems that you're enforcing it being unitary a priori. So are you able to formulate it as an effective field theory descending from a UV complete one?
A very important point that I didn't say, that Weinberg emphasized is that when we talk about effective field theories, you sometimes get the idea that, well, okay, maybe everything is up to some little corrections of order energy squared over cutoff squared and so on. Not unitarity. Unitarity is dead, perfect, sharp at all scales. There are many ways of seeing it, but essentially the only way to get imaginary parts of amplitudes is to put internal particles on shell. So if you have too low energies to produce the new particles, then the effects of the heavy particles do not show up in like slightly deforming unitarity. Unitarity is a rigorous property of the low energy effective theory. Unless, of course, you have enough energy to produce some stable massive particle. If there's some stable massive particle in the deep UV, then you'll miss that when the energies are big enough to produce them. But let's say all the particles in the UV are unstable, then the low energy theory would be rigorously unitary. So this S matrix, need to worry about like little corrections to unitarity if you're trying to describe low energy amplitude.
But does the amplitude approach? Yeah. Does the amplitude approach maintain unitarity at all energy scales, or is there a cutoff for the EFT?
No, but that's what I was trying to tell you is that it says that in the amplitude approach, the unitarity is an input, rigorous unitarity is an input, and so it is in effective field theory. In effective field theory, we don't have little violations of unitarity at low energies that grow with energy or anything like that. It's 100% unitary.
Okay.
After is different than what we can get in local quantum field theory. It actually saturates what you're allowed to do compatible with the principles of analyticity and so on. So in fact, local quantum field theory was a little too lazy. It could have done something like sharper and better. And string theory does that sharper and better thing when it comes to satisfying the sort of principles of analyticity and causality and so on. So it isn't like you find something which is like, aha, out of left field, you just cross out something and start over. It has never happened that way in 4 centuries. I've seen no reason to expect it's going to start happening that way now.
Then there's a question by Chester.
Yes, hello. And thank you everybody for the very fun talks. Nima, I have a question about this general approach to treating the scattering amplitude as the fundamental object. It seems that you're enforcing it being unitary a priori. So are you able to formulate it as an effective field theory descending from a UV complete one?
A very important point that I didn't say, that Weinberg emphasized is that when we talk about effective field theories, you sometimes get the idea that, well, okay, maybe everything is up to some little corrections of order energy squared over cutoff squared and so on. Not unitarity. Unitarity is dead, perfect, sharp at all scales. There are many ways of seeing it, but essentially the only way to get imaginary parts of amplitudes is to put internal particles on shell. So if you have too low energies to produce the new particles, then the effects of the heavy particles do not show up in like slightly deforming unitarity. Unitarity is a rigorous property of the low energy effective theory. Unless, of course, you have enough energy to produce some stable massive particle. If there's some stable massive particle in the deep UV, then you'll miss that when the energies are big enough to produce them. But let's say all the particles in the UV are unstable, then the low energy theory would be rigorously unitary. So
this S
we don't
matrix
need to worry about like little corrections to unitarity if you're trying to describe low energy amplitude.
But does the amplitude approach?
Yeah.
Does the amplitude approach maintain unitarity at all energy scales, or is there a cutoff for the EFT?
No, but that's what I was trying to tell you, is that it says that in the amplitude approach, the unitarity is an input, rigorous unitarity is an input, and so it is in effective field theory. In effective field theory, we don't have little violations of unitarity at low energies that grow with energy or anything like that. It's 100% unitary.
Okay.
Enrico,
Okay,
maybe we should also ask for questions also to the other speakers. I mean, to all speak also the.
Oh, yeah, sure. Of course, yes.
Maybe the next one,
See.
Martin Bauer.
Yes, hi, and thanks for a great series of talks. My question is to all speakers, but also mainly to Nima, because he mentioned it in his talk, and I wanted to follow up on this. It's this argument that you made between the correspondence of scattering amplitude for three-body scattering amplitude for gravitons and the Young-Mills squared that you can make, right? I want to ask whether there's some deeper physics behind this or whether it's just an accident. Because if you just on paper, that looks like it would also violate the Weinberg-Witten theorem if you could write down a theory of gravity as a composite. Like the,
So notice that this is most certainly not saying that the this is not saying that you can think of a graviton as two gluons on top of each other. You kind of can for the 3-point scattering, because if you think about 3-point scattering in Lorentzian signature, I mean, I didn't explain it in detail, but if you think about 3-point scattering in Lorentzian signature, everything is just collinear for massless particles, so you can just split in two. So in that way, the kind of obvious dumbest problem that you can't think of as a graviton is two gluons on top of each other, because when they scatter, they're going off in random directions, so they're not going together anymore, right? You can't think of that doesn't hold for 3 points because they're just going back and forth. But yes, but there is this correspondence between gravity and sort of gauge theory squared. Really, I think that the first place that it was vividly seen was in string theory, where you could understand closed strings, amplitudes for closed strings in a very precise sense as taking a product of amplitudes for open strings. This relation between sort of closed string and open string squared is a very deep thing in string theory. There's many aspects of it that are seen all over the place, but you can also abstract some of it away just for field theory amplitudes in this whole sort of program of Byrne, Carrasco, and Johansson on the sort of color kinematics connection, and anyway, ways of double copying field theory amplitudes to turn into gravity amplitudes and so on. So it's not a coincidence. There is something to it. It seems like the deepest origin is the relation between a closed string being two copies of an open string glued together.
And why wouldn't it violate Weinberg-Witten then?
Because it's not, in no sense we're not saying that the graviton is the bound state of two gluons on top of each other. And also the beyond the 3-point scattering, it's not just the product of the amplitudes. You do the product of the amplitudes and there's something else. So there's a relation between them, very simple relation between them, but it's not like literally one is a square of the other. So you're not imagining that the graviton is a sort of composite of two gluons, which would be insane because that these are weakly coupled particles. So I can't have them. As I said, if you even said that it's a composite of two of them, the second two of the gluons scattered, you're dead in the final state, right? Because they're no longer moving together. Nothing is binding them together. So it clearly doesn't work. But the relation is not just this direct product relation at higher points. On the other hand, it is some indication of a very sort of a fascinating structural relationship between gravity and Yang-Mills that's very difficult to see by staring at the Yang-Mills Lagrangian and the gravity Lagrangian. If you stare at those things, you would never suspect such a relationship. Even at 3 points, it's not remotely obvious from the gravity Lagrangian that the amplitude for 3 gravitons is the square of the amplitude for 3 gluons.
Thank you.
Okay, then the next one is Glennis, I think.
You have to unmute me. Oh, now I'm unmuted. First, I want to thank the speakers. They were all such wonderful talks, and it's mind-boggling to try to put one's head around what Steve accomplished. And, you know, as many of you all said, any fraction of those accomplishments would still be stupendous. I wanted to just add more, sort of more personally, I think, and these were things certainly the speakers alluded to, but I think it's really important to keep in mind also what kind of a person he was. In my life in physics, I so often, as we all have, I'm sure, encountered people who, rather than really grappling with some question, or would say, oh, it's obvious, or no, we know that's not possible. And Steve was so wonderful about both personally not putting people down, which lots of places people do that when they don't know. He wasn't afraid to say, oh, I don't know, this is worth thinking about, or kindly explain why they, you know, what the answer to your question was, without saying you're stupid not to know this thing. And that was in the olden days, that quality was even more rare, I would say. And then the last thing I just wanted to comment, I mean, besides also the fact that he was so willing to entertain that the common wisdom wasn't really necessarily the correct view. But the last thing I think also, I mean, it's too big an example for me at least to follow, but maybe others could. I mean, his work in the public sphere of writing about, I mean, if you haven't read his New York Review of Books articles, they're so wonderful. Well, like I say, to even minusculely try to aspire to be more like him is probably too much to imagine. But anyway, I just wanted to call people's attention who may not be that aware of his public writing and his wonderful books. Like The First 3 Minutes is still a phenomenal resource that I give to people. Anyway, we were so lucky to have all lived in the period where he was contributing to physics. Thank you all again for your wonderful talks.
I completely agree. I think Dreams of the Final Theory and together with Feynman's The Character of Physical Law are by far the best popular books on physics ever written.
So maybe Enrico. So the next question is from Sondata Bhattacharya. So let me. You're unmuted.
Yeah. Am I audible?
Yes, please.
Yes.
Yeah. So this is the question for Ed. I just wanted to know what he meant by saying that if you throw enough computer power, you can compute proton scattering.
The question I was asked was,
using.
The question was, with unlimited computer power, could a classical computer calculate proton-proton scattering? The answer to that is very clear, yes. Because with unlimited computer power, this is extremely unrealistic. The stress is on the word unlimited. With unlimited computer power, you could do Hamiltonian lattice gauge theory in real time and calculate any real-time process. Now, no one has even tried to estimate the computing power required because it would be unreasonable. In the real world, to actually do this is what you would probably need is a general purpose quantum computer. But if you ask, is proton-proton scattering accessible in QCD to a classical computer with unlimited computing power? The answer is certainly yes.
Okay, so thanks. If some data is satisfied. So I would again ask for questions also for the first two speakers. If there is anybody. But in the meantime, I do have a question maybe for the first three speakers or maybe all of them. So I think in the talk by Edward Witten, he said that in the review that Weinberg wrote in 1997, he had the point of view of regarding the standard model as an effective field theory. So I wonder when did people switch to this viewpoint? So when, or maybe if Weinberg was the first to realize this, and when this occurred, or maybe if there was a change of attitude of the community, and when this happened. So maybe either Edward or Howard can answer.
You're muted, Howard. Howard, you're muted.
Now you're unmuted, please.
We still don't hear him, I think. Yes, not muted, but we don't hear him, I think.
Howard, we're not hearing you.
He is not muted, so I don't know why. Howard.
Perhaps unplugging and replugging the headphones might do it.
Is that working?
Yes.
Yeah.
Okay, sorry. I was just going to say that I think it was beginning to happen in the 80s after the basic picture of effective field theory was in process, and also because string theory was beginning to, string theory and other ways of thinking of beyond grand unification and beyond were beginning to become current. So I know that certainly by that time, renormalizable quantum field theory was, we understood why it was not necessary to assume renormalizability to get the good consequences from quantum field theory. And the question is, it was just really what happened. I mean, another possibility, which nobody mentioned because it's kind of silly, but is, I think, logically possible, is that it's just turtles all the way down. And you have a tower of effective theories, and nature keeps surprising you as you go to shorter and shorter distances. Now, maybe that's impossible with gravity. I'm not certain, but
Edward, do you want to add anything?
Well, it's an interesting question whether that's impossible with gravity. I never really thought about that. Without gravity, certainly logically conceivable, and some have advocated it.
Right.
Especially people who are not particle physicists, sometimes hear them advocating it. My only other comment is that we shouldn't underestimate the role of grand unification in this, because grand unified theories were the original concrete examples where the standard model, not just hypothetically, but in real life, was a low energy effective field theory of something that was actually seriously put forward. and even today has a lot of attraction.
Thanks a lot. Thanks a lot. So any other question? I see Alberto Nicolis raise his hands. Please, Alberto, are you unmuted? Please.
Hear me?
Yes.
Hi, so I also have a question for Georgi. So, and I'm not sure exactly what Weinberg's viewpoint or contribution was in this, but when we have a weakly coupled theory with heavy particles and light particles, we define the low energy theory by, at least at the cartoon level, by integrating out the heavy particles, meaning really doing the path integral over the heavy particles. However, in cases of strongly coupled theories like EQCD, talk about the chiral Lagrangian for the pions, we don't have this description at hand. We don't have the pions as fundamental fields in the original Lagrangian. So there, as far as I can tell, the most practical approach is a bottom-up approach in which we parameterize the low energy theory in terms of the pions according to the symmetries. And then if we are strong enough, we match the parameters to the UV, to the predictions of the UV theory for certain amplitudes, let's say, at low energies. Now, is there a more direct definition of the low energy effective field theory that mimics the one that we have for weakly coupled theories? Is the question clear?
I'm not sure I understand the question, but let me first of all say that integrating out, even in weakly coupled theories, is not exactly the right thing to do. The right thing to do is to match at the boundary. And that looks like integrating out in simple cases, but in loops, it's simply more complicated than that. Beyond that, I'm not quite sure what you mean by the precise definition of the low energy theory, because it's phenomenologically fuzzy, since we will at low energies be always sensitive to some finite number of parameters and to a given accuracy. But what we can learn is what the symmetries are and what the leading interactions are, and something about the higher dimension operators.
So perhaps to be a little more explicit, so I'm referring, for instance, I've read recently your view, I think from the 90s, about effective. And my understanding about the subtleties of integrating out is that integrating out would be a perfect definition of the effective theory if we didn't perform the derivative expansion. I mean, if we kept the full non-local structure, then it's just an intermediate step to compute the low energy correlation functions, let's say. Sorry, the correlation function for the light field. The complications arise when we do the derivative expansion, because that changes completely the structure of the UV divergences.
Correct.
Okay, so now suppose we don't even do the derivative expansion. Okay, so we have the integrating out procedure now is a perfect definition of the effective theory for the light fields, let's say. Now, is there an equivalent definition in the case in which the light degrees of freedom are not even part of the fundamental Lagrangian, like for the pions, for instance?
Not that I know of. I mean, because I wouldn't know how to deal with such a general. I think one way of maybe what you're asking is whether there's a way of thinking directly about non-local theories, and I don't know of one.
Thank you.
Howard, I think maybe Alberto was asking, like, is this your question, Alberto? Like, we could imagine taking the ultraviolet theory, we don't have any pions, but putting some external sources that couple to the chiral currents. And then we can just ask what we get for the sort of we integrate things out, and then we can see that the effective theory that we get for the currents looks like it has sort of light poles in it that are mediated by pions and so on. And then we'd write, and we would try to write an effective, a different effective field. We can then integrate light things in order to reproduce all of those correlation functions.
Something like
Is that the sort of thing you were imagining? Okay. Yeah.
Like that, meaning what you're proposing with external currents will be now the generating functional of certain correlation functions, right? And so the Legendre transform of that would be more like the quantum effective action associated with the chiral Lagrangian, would not be directly the chiral Lagrangian, something like that.
Yeah, but then you transform it back and see the chiral Lagrangian in a derivative expansion. I think it sounds like very much the same thing. It doesn't matter that, I mean, it doesn't matter that you don't see the pions there. If you're an experimentalist, you would just couple to some external sources that produce the pions anyway, and you don't know how they're, yeah. So, yeah.
I mean, one thing that Steve said early on in his career that I've never really understood well enough to follow up is this, in a sense, this notion of integrating in. And he showed that one could add fields corresponding to composite particles and reduce make the theory more perturbative. And that's a very attractive idea, but I don't know of anybody that's ever really made it work.
Thanks.
Okay, I see that there are 3 other questions. Maybe we can quickly go with all of them, and then we will conclude. So Alexander Westphal, please.
Yes. You hear me?
Yes, we do. Please.
Okay. Yeah. Thanks, Nima. I mean, it's just there was a discussion in the chat, and I felt maybe I just put it to Nima. We were discussing about your argument about review of Weinberg's argument of the anthropic reasoning for the CC. You had this toy landscape. Of course, that argument depends on the prior of how the small lambda back here close to 0 are distributed. And of course, it's flat number frequency and number distribution. But can you estimate, like, for instance, say, Torre vacuum eternal inflation plus time?
Yeah, maybe I'll make a few correct statements. One of them is that Weinberg, one of the greatest things about him, in this context especially, is that he managed in all these like stupid 10 years of dumb philosophical polemic debates with essentially no content to avoid it entirely, having contented himself with having made a prediction, right? And having made a correct prediction. Of course, we don't know how to think about the measures, how to think about all of that stuff. That's all related to the business about how the landscape is populated. However, there is an aspect, which that's what I was stressing, is not philosophy, which is simply that if you take that dumb model with like n scalars, it makes it possible without any fine adjustments of the parameters to find a vacuum which looks like ours. It's at least possible. You don't have to fine tune anything. It's at least possible. They exist. Once they exist, and they just exist, I mean, it's just a simple, usual statistical argument. Anyway, literally in that model, there's a little bit more going on because you have to make sure that the central limit theorem in that model would tell you that the distribution gets more and more sharply peaked around the mean. You have to make sure that that actually overlaps 0. So you have to do a tiny bit more work in that model to make sure that it overlaps 0. But if it overlaps 0, you have a flat distribution. And of course, that flat distribution of vacuum, how that translates into whether or not it's realized and how it's realized, that's a whole morass that I don't even want to touch. It just makes it possible to find some. And then past that point, I mean, it's just you can say all the mumbo jumbo you want, but Steve said the reasonable thing. He said, look, if this is the explanation for why the cosmological constant is small, it shouldn't be too much smaller than the value that would rip us apart. If it was 100 billion times smaller than that, then it's not the only explanation. There has to be something else explaining it, right? So it's just at that level. But it's not a theory. I like to think about the sort of landscape picture as a cartoon. It doesn't even deserve the dignity of a theory yet. It's kind of a cartoon for what a theory might look like. But let me just make one more point, which is that it's conceivable that the landscape looks in such a way that totally independent of any issues about measures, you can still make interesting predictions where, for example, solving the cosmological constant problem forces you to do some tuning for the hierarchy problem. So let's say, just as a concrete example, there are two different regions in the landscape. In one of them, there's a low energy SUSY, everything is natural, beautiful, perfect. If you're particle physicist, you want to live there. But you count and you count and you count, and there's 10 to the 40 vacua there. Okay. Then there's another region in the landscape where the SUSY is broken at much higher scales. It's not natural from the particle physics perspective, but in that region there's 10 to the 200 vacua. And let's say those are the only two regions there are. This region where you have low energy SUSY with 10 to the 40 vacua, this other funny region with 10 to the 200 vacua. Then even though as a particle physicist, you might want to live in the place which is natural from the point of view of the Higgs, there just aren't enough vacua there to solve the cosmological constant. So you might be forced to go to this other regime where SUSY is broken at much higher scales, but simply in order to find a vacuum with a small enough cosmological constant, you could be forced to tune the Higgs mass. So, and those are examples where you can make a prediction without any issues about measures, et cetera, et cetera. So we don't know that the landscape has these favorable conditions to be able to do that, but it's not a priori guaranteed that it doesn't.
Mm-hmm. I agree. It's a good point. It's actually a good example for something that decouples from the measure.
Okay, so Kelly Stelle, please.
Yeah, hi. I have a question, I guess, mainly for Ed, regarding Steve Weinberg's revised attitude towards renormalizability. So if I certainly agree with Weinberg and Kim Gomez that you can renormalize a non-renormalizable theory, you just keep on doing it forever and ever and ever. But the question is really, to what extent is renormalizability still a guide at low energies for what you should look at? And a classic example would be gravity itself, for which we don't, the low energy Einstein-Hilbert theory is not renormalizable. So what is one supposed to do with it? Or another example would be a nonlinear sigma model for pions, not yet knowing about an underlying QCD. If you just say that any good theory, maybe there's a hidden word, acceptable or good, that the low energy theory should be renormalizable. Is that what he was thinking? Or can it be articulated more clearly?
Well, one statement is that the low energy theory looks renormalizable regardless of what's happening at short distances. But our ability to even know about gravity is exceptional because it's unrenormalizable. Obviously, only because gravitational forces add, we know that gravity exists. Anything nearly as weak as gravity, if the charge is canceled, we wouldn't know about it.
So suppose I give you a nonlinear sigma model for pion theory, right, which you, of course, know a lot about, and you didn't yet know how to derive it from an underlying QCD. What would its non-renormalizability tell you to do? Well,
an unrenormalizable theory, according to Weinberg, is good up to a certain energy at which there's a cutoff, at which you need a better theory. So I'm not sure, in your example with the pions, are we supposed to know maybe from experiment that the low energy theory is breaking down below a GeV? Then we would know that at a GeV we need a better theory.
Yes, in the nonlinear sigma model, you've got a dimensional parameter, which is the pion, which is F pi, and F pi sets the scale at which things must go wrong, or 4 pi times F pi, or whatever it is. But there are dimensions in.
Both of the examples have the feature that ignoring the leading irrelevant interactions, the theory is free.
Well, that's certainly true, and that's a limit.
So in that sense, that the leading thing is renormalizable in the most trivial sense of being free. And so all of the first interesting interactions are coming from the irrelevant couplings. In the case of gravity, as Edward says, we notice it because gravity adds up. For pions, we notice it because pions couple to nucleons, and we've scattered them in experiments and so on. So, yeah.
I certainly agree that they're free at the leading order, but that isn't much of a guide then. If every acceptable theory is supposed to be renormalizable at low enough energies.
I don't think that Weinberg wanted effective field theory to be the last word. He was explaining that everything we know can be described by effective field theory. But in that remark I quoted at the very end of the third of his lectures that I talked about, which is the one from just a couple of years ago, he was encouraging the younger generation of physicists to discover what's behind the effective field theory that we observe.
Let me just add that the other special thing about pions is that they're light. And so there is a region where the effective field theory is actually useful. And in that may not always be the case.
Okay, thanks.
Okay, we have one last question. Matthew Hedrick, please.
Hi, thanks. And I apologize if this was already addressed because I missed the first couple of talks, but I was wondering if any of the speakers had any comments on Weinberg's idea, getting back to this issue of non-renormalizability of gravity and so on, Weinberg's idea of safety for gravity, which is something that at least in the US, we don't hear too much about, but I think there are groups in Europe that are actively pursuing that. So if there's any comments about that.
The question is about asymptotic safety?
Yeah.
Well, I have a comment about it. That's a question. If there's a fixed point that includes gravity, usually a fixed point is at least a scale invariant theory. But in local quantum field theory, it turns out that fixed points are conformally invariant. That's rather subtle. If there's a fixed point that involves gravity, does one think it's only scale invariant, or does it turn out to be Weyl invariant? I actually never heard Weinberg express an opinion about that. We had a discussion once where he could have, but he didn't.
Okay, so I think it's time to wrap up. So Stefania, are you around?
Yeah, I'm here.
Okay. So do you want to
I never moved.
say the final words?
Okay. I see that there are a lot of questions still in the chat. So if you want, we have, as always, open our Q&A session on the GGI webpage. So you can use this facility to write your question, and then we will deliver the question to the speaker. Also, in the chat, someone asked me if the slides are available, and I said yes, but I have to ask the speaker to send the slides to us, and then we will publish the slides on the page. As a final thing, I just want to thank Elizabeth, she is with us, and she's attending our session. So it was an honor for us to have her with this special celebration. And of course, I ask all of you for attending this session and make all this celebration very, very exciting, and I think very useful for the young researchers who were here attending the session. So have a good evening for us and day for all the other, and thank you again for being here.
Thank you,
everybody.
Ciao a tutti.
Thank you.
Thank you.
Ciao.
Thank you, everybody.
The GGI Tea Break program go on. So
Thanks,
stay tuned with our webpage.
Thank you very much. Thanks for the invitation, guys.
Thanks to
Bye-bye
you.
now.
Thank you.
Bye.
Bye.